All right, welcome back. Last time we met, we talked mainly about ecosystems. And we talked about the structure of ecosystems and also the functioning ecosystems. And we said one of the functions in ecosystems is energy flow. And we looked at how energy might flow through an ecosystem, and we want to get more into that today. So we're going to talk a little bit about food chains and carrying capacity. So let's go over the handy dandy document camera. And I put together a little drawing. And if you diagram biomass in an ecosystem, you generally see kind of a pyramid like this. And this pyramid shows your basic food chain. So ultimately the energy first comes from the sun and is picked up by green plants, the producers. And then that energy can flow through the food chain and reach primary consumers, so plant-eating animals, then maybe secondary and even third primary consumers. Now, I want to get at why this has the shape it does. So we'll go back over to the slideshow here. So if we're talking about biomass or this energy pyramid, why does it have that shape? Why does it have the pyramid shape? Well, one reason it does is because of respiration. So when we talked earlier in the semester, we talked about that organisms need to use some of the energy that they capture. But some of that energy is eventually used for things like maintenance metabolism. They have to maintain their structure. Other uses of that energy are for active metabolism. So that's moving around, avoiding predators, and catching more food, so bringing in more energy. So that's the main reason. So some of that energy is lost. But ultimately, there's another reason. Very related. It's the laws of thermodynamics. So if you remember, second law of thermodynamics, no energy transformation or transfer is 100% efficient. You always lose some of that energy as heat. And that's what's going on in this food pyramid. That active and maintenance metabolism, that energy eventually turns into heat. So the second law really constrains systems. It makes it so only a certain portion of that energy is available to the next level. And generally, 90% of the energy is lost per level. Only 10% of it passes on. And that's an average that can vary. Okay. Now, I want to give you guys a little bit of vocabulary to remember. One of the bits of information is gross production. Now, gross production is all the energy fixed or assimilated by an organism. So it's everything that an organism takes in that doesn't really go out the back end. That's the gross production. Now, the other vocabulary is net production. That's after maintenance and active metabolism. So that's what's left over after that goes to growth, reproduction, and storage. That's what's available. And again, second law of thermodynamics. Now, let me talk about a few energy issues. One is ectotherms versus endotherms. So cold-blooded organisms versus warm-blooded organisms. So how might an ecosystem differ when it comes to energy flow? Let's go back to the document camera here. And I got two little drawings here of what might happen if you had an ecosystem that was dominated by endotherms, right here, versus ectotherms. Now, endotherms heat themselves, so they require a lot of energy to do that. So what you might see is more energy loss, so it quickly decreases the amount of energy available to the next level, and because of that, it might not go as high. Now, ectotherms, if you had an ecosystem dominated by ectotherms, you'd see less energy loss per level. It might even go higher because there's more available. So that's how an ecosystem might change, and according to the types of organisms living in it. And there's been some research that showed that dinosaurs favored this kind of ecosystem. So that suggests that those guys were really warm-blooded. Okay. Now, another energy issue we can look at is vegetarians. I get a lot of vegetarians in my classes, and you can argue that being a vegetarian from an energy perspective is more beneficial. So if I put back that original drawing I did, and we look at it, if you are a vegetarian, you're dining on the producers here. So there's more energy available to you here. You can support more people at this level. If you went one higher, maybe these are cows, now you're operating up here, you support fewer people. So that's a decent argument for being a vegetarian. All right, another energy issue. Fisheries. Fisheries, if we go back to the document camera again, fisheries have gone through some big changes over the years. Initially, we were fishing very high on the food chain, but these fish have disappeared. We have continued to fish down the food chain to get at the smaller but more populous fish down here. So that's another issue. Okay. Now, carrying capacity. What's that? What's that? It's really how many of a certain type of species you can put in a defined area. And if we diagram it, we go back to the document camera, it might look something like this. You got the numbers of organisms here and over time. And first the numbers might increase, it's driven by exponential growth, and then this carrying capacity slows down that growth. And that's due, what is controlling this? It's the energy available, so the food, the water. It can also be a density-dependent factor such as disease. You get more organisms, there's more chance of disease. So density-dependent factors are something you should understand. Density-independent factors might be storms killing off groups. It doesn't really matter how many you have. Now, how often do you see this in real life? Not often. Probably because this carrying capacity changes a lot. All right. So we talked a little bit about density-dependent versus density-independent. Again, the density-dependent really controls the carrying capacity. All right, I got a problem for you. We're going to work this out and get back to this on the next segment. So first, I want you to try to calculate this. In New York City, we have about 800 square kilometers of space to work with, about 8 million people. And the Earth-land surface area is about 150 billion square kilometers. So the problem I want you to solve is, if we packed everyone at a density like we find in New York City, all over the Earth, how many people could we fit? So next segment, we'll get back to that, and we'll talk a little bit about that. And we'll see what your answer really means. So thanks a lot, and see you next week, or next time.